So the next example we'll look at is we want to construct a finite automata which accepts strings which contains exactly two A's. But the two A's need not be consecutive like the previous example that we have seen. Right? So for example, I want basically B star A. Again, I could have B star A, B star. So here it has exactly two A's and any number of B's that I don't care of. Again, as we have seen, B star basically implies epsilon, B, BB, BBB, etc. So on and so forth. Any of this. It could be any element in this set. Okay, if you think of this as a set, any element in this set could be used instead of B star. Now let's start constructing it. Okay, so what all will be there in this language? Obviously AA will be there in this language. So let's start constructing the finite automata for this. So I am at Q0. Again, once you do enough examples, this will be trivial, to be honest. Okay, so this is Q2. So AA is accepted now. Okay, so this is good. So can we just be done with three states? Let's see if three states are sufficient. Again, we don't know. So let's go with the flow. So what if I get BAA? This should also be accepted because it has exactly two A's, which means if I get a B here, look at this, BAA is also accepted. Similarly, BBAA should also be accepted. So any number of B's followed by A will be accepted. Similarly, what if I get BABA? This should also be accepted. So if I get BA, BA. So this state basically says that I've seen 0 A's. This state says that I have seen, if you reach this state, you have seen 1 A. If you reach this state, you have seen 2 A's till now. Okay, that's the logic here. Now, once you have seen 2 A's, any number of B's that you see, you don't care about it. Okay, so for this state, both transitions are done. For this state, both transitions are done. For this state, if I see an A, what happens now? Okay, what if I have AAA? This should certainly not be accepted, right? Because it has 3 A's. We want exactly 2 A's. Okay, so if I get an A now, I should go to a dead state. Look at this. This is a dead state because the moment I see 3 A's, I should never be able to accept it. Right? Very simple. If this is a dead state, what happens if I get A or B after that? Once I've seen 3 A's, I should never accept it. Hence, I go to a dead state. Very simple example again. Right? Very, very simple example. So that's it. I need 4 states. I cannot get away with just 3 states. I needed the dead state to account for the fact that I should not accept AAA or anything that has 3 A's instead of just 2 A's because I want exactly 2 A's here. That's the task. Right? See how we are leveraging dead states again. Okay. So what if I want at most 2 A's? Okay. What does at most 2 A's means? 0 A's, 1 A or 2 A's, but not 3 A's. Okay. This is one thing that I want to now do. So now let's see. Again, this will be a simple extension of this concept because if I'm here, it means I've seen 0 A's. If I'm here, I've seen 1 A. If I'm here, I've seen 2 A's. If I'm here, I've seen 3 A's now. So what if I just draw the same diagram, but make Q0 and Q1 also final states? Then if I have if I have 0 A's, 1 A or 2 A, I'll accept it. The moment I see the third A, I'll not accept it. Right? So it's a very simple extension to this logic. Okay. So wherein let me start drawing this, right? So I have Q0, A, Q1, A, right? So this is 2 A's. This is 2 A's. This is 1 A. This is 0 A's, right? If I keep getting B's, perfectly all right. If I keep getting B's, perfectly all right. If I keep getting B's, perfectly all right. But the moment I get 3 A's, look at this. This is exactly the same thing as this. This diagram is exactly the same as this diagram, except that Q0 and Q1 are also final states because I have to accept even if you have 0 A's or 1 A also, right? Of course, this will be a dead state because the moment because it says at most 2 A's, I cannot have 3 A's. The moment I have 3 A's in my string, I reach here. Hence, this should be a dead state. Remember, this should be a dead state because I should never be able to come back. I should never go to an accepting state after this. Simple extension. See how we have extended this concept of exactly 2 A's to this concept of at most 2 A's. Again, this flow is very important, right? First, we start off with exactly 2 consecutive A's. Then with exactly 2 A's. Then with at most 2 A's. Now, what if I want to do at least 2 A's? How do I change this? Again, this should be easy, right? At least 2 A's. Okay, let's start drawing this. Okay, again, we'll continue to build on top of this. If I reach here, I have 2 A's. Now if I have, what does at least 2 A's means? 2 A's should be accepted. 3 A's also must be accepted. 4 A's also must be accepted, so on and so forth. But 0 A's must not be accepted. 1 A should not be accepted. So let me continue on this diagram itself. Okay, so let's actually continue on that flow. And this is my Q0. I have 0 A's now. This is my B. Okay, I'm just trying to replicate what we have seen earlier, right? So this basically accepts, till now it accepts 2 A's. Good. This accepts 2 A's. This state both transitions, this state both transitions. If I keep getting B's, I can be here. Now comes the interesting part. If I get 3 A's, I should accept 3 A's, right? So AA. See, for this state, if you notice, for this state, both transitions A, B are done. For this state, transitions A, B are done. For this state, only transition B. Where should transition A go to? So we should accept AAA, right? AA. So if it is A also, I should accept it. Right? So the moment I've seen 2 A's, if I see any number of A's or B's now, I should accept them. So here I didn't need the dead state. If you notice, here I don't need the dead state. Okay? Because this anyways, by the time I reach here, it means I have 0 A's. By the time I reach here, I've seen just 1 A. I'll not accept these two. Okay? The moment I need 2, 3, 4, whatever it is, I don't need the dead state here. Right? So I can get away with just 3 states in this case, unlike with at most 2 A's where I need a dead state to keep track of 3 A's, 4 A's, 5 A's, because none of them should be accepted. Right? So again, at least and at most, very interesting concept. Now let's go slightly one step further now. If I want even number of A's, okay, there are 3 cases here. Even number of A's, odd number of B's. Okay, let's start with even number of A's. This is simple. Okay, again, we'll come to the modulo arithmetic in a little while, but let's start with even number of A's first. Then we'll learn a lot of things about modulo stuff. Okay, what is even number of A's? Okay, so I have 0 A's. Okay, I have 0 A's. Okay, so what does this mean? Okay, let's write this down. So here, what have we seen here? We have seen 2 A's, 3 A's, 4 A's, etc. Here, what do I want? I want 0 A's, 2 A's, 4 A's, 6 A's, 8 A's, so on and so forth. I should accept all of them. Now, how do I solve that problem? Okay, let's see. So this is my initial state, Q0. So I'll track this as seeing 0 A's, hence my final state. Let's start with this. Okay, now I've seen 0 A's now. Okay, if I see 1A, look at this. If I see 1A, I should not accept it. So this transition basically tells me that I've seen an A. Now, what happens if I keep seeing B's? That's perfectly okay. If I keep seeing B's, there is no problem with it. Okay, if my words only consists of B's, no A's, then it has 0 A's, and 0 is an even number, so I can continue being here. Now if I see 1A, how many ever B's I see now? See, this state basically keeps track that I have seen 1A now, 1A. This keeps track of 0 A's now. Now instead of it tracking 0 A's and 1 A's, why can't I make this track even A's and this track odd A's? Because even and odd are only 2 cases, right? I have 2 cases. What if I have 2 states, each state tracking the even odd case? So what if I make this even? What if I make this track even? What if I make this track odd? We've seen this type of example earlier also, right? So for example, if you notice, we have looked at even number of occurrences of string AB. Look at this, odd number of occurrences of AB. We have seen similar example. Okay, so we have this state tracking all the even occurrences of AB. This state tracking all the odd occurrences of AB. Now, similarly, can I just have a very much simpler thing? Now, if I've seen 1A, what if I have 2 A's? I should accept it. So, if I have 2 A's, A followed by A, or A followed by any number of B's followed by A. That's it. So, for this state, both transitions on A and B are defined. For this, transition on A, transition on B is also defined. Very simple example. So, this is keeping track of even number of A's. This is keeping track of odd number of A's. So I just needed 2 states here. Very simple example, right? Very simple example. Similarly, if I want odd number of B's, let's say, suppose if I want odd number of B's, slightly different example, but very similar. Look at this. Q0 cannot be there. Okay. So suppose again, very similar diagram to this. Okay. So I've seen 1B, which means it should be here. I don't care about A's. I don't care about A's. So this is now tracking odd. This is now tracking even number of B's. Okay. If I have A's, I don't care. Now if I get a B, I will go here. Simple. Just with two states, I'm again done. Again, this diagram and this diagram are very similar. Here, since we wanted to accept even number of A's, Q0, because this will have 0 A's also. That's why this is the final state. Here, Q1 is the final state. Right? Very simple concept if you think about it. And each state is tracking whether I have even number of B's or odd number of B's here. Very, very simple example. Now let's go one step further. This is where the fun starts. What if I want the number of A's to be 1, 4, 7, 10, etc. Now if you look at this, okay, so let me write some very basic stuff. Okay, 0, 2, 4, 6, 8. Okay, you can write this set as 0 mod 2. So what does this mean? It means the set of all the numbers which if you divide by 2, you get a 0, you get a remainder of 0. So mod basically means modulo. Okay, you know the modulo operator, right? We learned in C programming language. If you do 4 modulo 2, this is equal to 0, right? Because the remainder on dividing 4 with 2 is 0. Similarly, 5 modulo 2 equals to 1. So we can represent a set of all even numbers. So the set of all even numbers, you can write it as 0 modulo 2. Because even numbers, when you divide with 2, you get 0. Similarly, all odd numbers, I can write them as 1 modulo 2. Because when I divide odd numbers with 2, I get a remainder of 1. So imagine if I have a set like this, if I have a set of numbers like this. Okay, my number of A's can be 1, 4, 7, 10, etc. So if you notice the pattern here, all of them, when I divide them with 3, I get a remainder of 1. 3 divided by 1, remainder is 1. 1 divided by 3. 4 divided by 3, remainder is 1. 7 divided by 3, remainder is 1. 10 divided by 3, remainder is 1. So this is called as a modulo arithmetic. This is called as a modulo arithmetic. Okay, this is called as a modulo arithmetic. Now, if I want the number of A's to be 1, 4, 7, 10, etc. Or in other words, if I want it to be 1 mod 3, how do I construct it now? Okay, very good example. Here, instead of even odd, I have these 3 cases. Okay, so again, actually there are 3 cases. When you divide any number by 3, okay, you can have a remainder of 0, you can have a remainder of 1, you can have a remainder of 2. There are 3 possibilities, right? See here, we got away with 2 states because there are only 2 possibilities. When I divide with 2, I can either get a remainder of 0 or I can get a remainder of 1. So I got away with 2 states here. Now I have to keep track of 3 states. If the current number, of A's is exactly divisible by 3, if the current number of A's is divisible by 3, when I divide it with 3, I have a remainder of 1, I have a remainder of 2. Look at this, look at this whole concept. This is very, very important. Okay, this modulo arithmetic based finite automata are super useful actually. Okay, let's actually construct the solution here. Okay, so first 1A I should accept it, right? So let's start there. Okay, 1A I want to accept it. 1A I want to accept it. Very good. 4A's also see this Q0 basically, again, the way I'll design my whole thing is Q0 is when the number of A's is divisible by 3. Q1, I'll reach this state if the number of zeros is divisible, when I divide with 3, I get a remainder of 1. Okay, so similarly, if I get 2 A's, I'll go to this. Okay, that's how I'm keeping track of it. Q0 corresponds to this state. Q0 corresponds to this state. Q1 corresponds to this. Q2 corresponds to this. That's how I'll design my whole architecture. Right? So now I want 1, right? Look at this. If I get 1A, that should be my final state. Right? Just a single A, because number of A's can be 1. So this case is taken care of. If the number of A's is 4, even then I should do it. So 2 A's. What if I get the third A? Look at this. If I make my third A point like this. Okay, look at this. So now will 4 A's be accepted? A. Yes. Right? Because if I have, again, the logic here is very important. When I'm in this state, I have seen 2. I've seen either 2. Look at this. Okay, let's write this down, right? If I'm in this state, I have seen either 0 A's, 3 A's, 6 A's, 9 A's, 12 A's, so on and so forth. When I'm in this state, I've seen 1A, 4 A's, 7 A's, 10 A's, so on and so forth. The remainder is 1 here. Here the remainders will be 2. So 2 A's, 5, 8, 11, so on and so forth. Okay, if I've seen 2 A's, I should be here. If I've seen 5 A's, I'll be here. The way we have designed it. Now, what about B's? We have to handle B's also, right? I actually don't care about B's. I'll continue to be in the same state. If I encounter B's, I'll just stay in the same state. Only when I encounter A's, because I want to keep track of number of A's. If I'm in this state, I either have 0 A's, 3 A's, 6 A's, 9 A's, 12 A's, etc. If I'm in this state, I have 1, 4, 7, 10. If I'm in this state, I have 2, 5, 8, 11, so on and so forth. Or in other words, if I'm in this state, I'm in 2 mod 3. Okay, this set is nothing but 2 mod 3. This set is nothing but 1 mod 3. Okay, this set is nothing but 0 mod 3. Right? So now to build this set which is 1 mod 3, because 3 has, when I divide any number with 3, there are 3 possibilities. I need 3 states here. So 3 states I need. Again, just like in even odd, there are only 2 possibilities. When you divide with 2, if you get a remainder of 0, this means it is even. When you get a remainder of 1, it means it's odd. You have only 2 states or 2 logical states, and hence you're tracking it here. Here I have 3 possibilities. Remainders can be 0, 1, 2. So I'm designing it like this. Okay, again, this modulo arithmetic based models are super duper important. Okay, so let's go one step further. One more example like this, right? So 2 mod 4. So what is 2 mod 4? 2, 6, 10. Again, add 4 to it, add 4 to it, so on and so forth. Again, I have mod 4. As we have seen from the logic here, if I have mod 2, I needed 2 states. If I have mod 3, I needed 3 states. For 4, what all reminders are possible? 0, 1, 2, 3. So I need to have 4 states, right? So this state is my 0 mod 4, right? So this state will be 1 mod 4. This state is 2 mod 4. This state is 3 mod 4, right? And when again, so I want B's, right? Not A's. So B, B, B. From 3 mod 4, if I see one more B, right? So I'll go here. So here now again, let's write this down, right? Let's write this down very easily. So 0, 4, 8, 12, so on and so forth. Here this will be 1, 5, 9, 13, so on and so forth. Okay, here it will be 2, 6, 10, 14, so on and so forth. So this has to be my final state. What about this? 3, 7, 11, 11, not 15, right? So this is 3. Yes, 15. So on and so forth. Yeah. Now what about A's? A's will continue to be here. I don't care about A's. I only care about B's in this case. A's will continue to be here. That's it. See how quickly we can construct for these modulo operators. Very quickly. You can literally write it down in like 10 seconds. So how many states do I need? I need 4 states to keep track of each of these. 0 mod 4, 1 mod 4, 2 mod 4 and 3 mod 4. That's it. Very, very simple example here. Now, if you have any, so as a generalization, if you have anything R mod n, look at this, if you have R mod n, okay, or in other words, if the number of A's, again, we wrote this, right? If you have a word, WA basically means, so this basically means number of A's in W. If number of A's in W is R mod n, here look at this n, you will have n states, Q0, Q1, Q2, so on and so forth. You will have up to Qn minus 1. Just look at this example. See, n is 4 here, n is 4 here. You have Q0 to Q3. You have n states. And you have n states, right? You have QR somewhere here. This becomes your final state. This becomes your final state. Look at this. You had 2, so Q2 became a final state. Very simple example. And you will have all these transitions on A's here. All these transitions on A's. All transitions on A's like this. All transitions on A's like this. The last one will connect to the first one cyclically. Look at, this is like a circular linked list if you want to think about it. Again, that's how I think about it. Okay. So again, all your B's, nothing changes. Because by having B's, your number of A's don't change. Sorry, this is B. By having B's, your A's don't change. So as a generalization, if your number of A's, okay, which can also be represented mathematically like this, if the number of A's is R mod n, you can construct a finite state automata with n states corresponding to each. See, because you have R mod n here, n can have reminders of 0, 1, 2, so on and so forth up to n minus 1. And hence you have n states. This is reminder 0, reminder 1, reminder 2, reminder R, reminder n minus 1. You can't have reminder n, right? Because This is n itself. If it's exactly divisible by n, you'll get remainder of 0. Very simple. Again, this is a generalization of what we have just learned in the last couple of examples. Very simple concept here. Okay. Now let's go one step further. Okay. So if I want to now construct a minimum finite automata that accepts all strings where the length of the string equals to 3. Slightly different. See, look at this. What did we do here? The number of A's is what we saw here. Now we want to construct the length of the string itself equals to 3. Anything that is of length more than 3, I don't want to accept it. Very simple. This is also a very simple case. Okay, the length of the word. This has to be read as the length of the word is 3. Again, this should be very simple. So Q0, Q1, Q2. So right now, when I'm here, the length of the word that I've read is 0. Okay, the length is 0. The moment I arrive here, whether I read A or B. See, let's assume my alphabet is A or B. That's what it says. So whatever I read, when I'm here, my length of the word is 0. When I'm here, the length of the word is 1 because I've either read A or B. When I reach here, the length of the word is 2. So I want the length of the word to be exactly 3. So what do I do now? So now when I read A or B, by the time I reach here, the length of the word that I've read is 3, exactly 3. The moment I get 4, what should happen now? See, this is my final state now. This is my final state. Because the moment I reach here, it means I've read my length of the word is exactly 3. Right? Now, if I get A or B now, this should be my dead state. Because the moment I reach here, I get 4. Look at this. The moment I reach here, this is the dead state now. The moment I reach here, right, I have 4, 5, 6, 7, any number of symbols in my word. I want exactly 3 symbols. The length of the word to be exactly 3. So that's why I've designed this. Very simple example here, if you notice. So if I want to design a system where I care about length of the word to be equal to some n, right? How many states do I need now? Because for 3, I needed 5 states. 1, 2, 3, 4, 5. Right? For 3, I needed 5 states. So I need 3 plus 2 states here. 3 plus 2 states. So if I need n here, it will be n plus 2 states. Just as a generalization of this. Okay. Okay. 1 second. Can I get away with 4? No, I can't, right? Can I get away with 4 states? Let me think. Okay. So I have, this is my initial state. I always arrive here. I can't run away from the initial state. I need the first state, second state, third state. Anything more than that, yeah. This is what I need here. I can't reduce this by 1. Now let's take this example. If I want the length to be less than equal to 3, what do I do then? See, this says, see, in such a case, okay, let's draw this first thing, right? Let's draw this first thing. Okay, let's draw this. Okay. I'll change this slightly to get the solution to this. Okay. So again, A comma B, Q2. Again, A comma B, Q3. Let's not put the final states yet. Okay. A comma B, Q4. Okay. So what do we have now? This means 4 or more states. So this cannot be final state. This will be a dead state as usual. If I'm here, the length is 0. Hence it should be accepted because length is less than equal to 3. Here length is equal to 1. Here length equals to 2. Here length equals to 3. So all these 4 states become final states. This becomes a dead state. Small modification on this. That's it. What if I want length to be greater than equal to 3? What do I do? Again, that's very simple, right? You make this the final state. Okay, let me draw this. Okay. Again, very simple case. Okay. So 0, 0. Say when I'm here, the length of the string is 0. When I'm here, the length of the string is 1. When I'm here, the length of the string is 2. Right? When I'm here, the length of the string is 3. What do we want? Greater than equal to 3. Okay. So here, the length of the string is 3 now. Okay. Anything else, if it is greater than equal to this, right? See, look at this. Here, the length of the string is 3 and hence, look at this, is greater than equal to 3. Okay. The length here is equal to 0. Length here equals to 1. Length of the string here equals to 2. Length of the string here equals to 3. But I also have the self loop. So if I keep seeing more, it will continue to be here. So length equals to 3, 4, 5, so on and so forth. So this is my final string. This is my final state. Very simple example. Okay. Here, I wanted to show all these examples at one place because from one of them, you can easily arrive at the others very easily. Remember, there is one important caveat, important borderline case here. Here you have 5 states. Here also you have 5 states. Here you have only 4 states. in the minimum finite automata. Okay, let's not forget that basic thing. You can get away with just 4 states here. Because 3 or greater than 3, I don't have to create a dead state here. Right? Because I have the greater than equal to, I don't have to create the dead state. Okay, so now let's look at one more example. Again, we've already seen, so if the length itself, what have we seen earlier? We have seen the case of number of A's being even and odd. Okay, we have seen this example. But what if I want the number of A's, what if I want the number of A's, so the length itself to be 0, mod 2, which means the length has to be even. How do we construct this? Okay, the length has to be odd. So this should also be easy. Let's start constructing it, right? So 0 mod 2 basically means 0, 2, 4, 6, 8, etc. Since I want to track even odd, I should be able to do it with just 2 states, right? So Q0 and Q1. I start here. When I start here, my length is 0. So I should accept this. So if my length is, okay, let's see, A comma B. The moment I reach here, the length of my word is odd, right? So now if I go back here with A comma B, my length becomes even. So this will take care of your 0 to, so intuitively, this is your even length state. This is your odd length state. That's it. Very, very simple case. Okay. So you have both transitions AB, you have both transitions AB. Now for this problem, what do? You just make this your final state. Look at this. You want the length to be odd. How do you solve that? That's very simple. Anyway, this is tracking even length, right? This is tracking odd length. So make the odd one the final state. Make the odd one the final state. That's it. Because this is tracking the odd length. This is tracking the even length. You want 0 mod 2 here. You want 1 mod 2 or odd. Right? So that's it. You just, instead of the even tracking state to be the final state, you make the odd tracking state to be the final state. That's it. You're done. It's that simple. Let's look at slightly more complicated examples now. Let's mix the modulo. So in this case, what are we doing? We are mixing the modulo part and the other part, substrings and startings and things like that, right? So let's look at this. Here, what do I want? I want my strings. I want a minimum automata of A's and B's that starts with A. And look at this. This is logical and. It should start with A and the length of the string itself should be 0 mod 3. What is 0 mod 3? 0, 3, 6, 9, etc. So the 2 conditions that we have to satisfy. Okay, let's start building this. Okay, so it has to start first. It has to start with A. Okay, so which means I have my Q0. Only on transition to A, I'll go to some other state. If I start with B, again, we have seen how to construct strings that starts with A. If it starts with A, I'll go to a reasonable state. If it starts with B, I'll go to a dead state. Okay, I'll go to a dead state. Okay, so this is my dead state. Okay, so now if I get A or B, I don't care. Because I'm starting with B, because both the conditions, it's a logical and, which means it should start with A. If it starts with B, this is a dead state for me. Okay, I'll never accept that. Okay, first part is done. Now let's go to the second part. Okay, so this component, this brick or this set of states, if I reach here, it means the strings are starting with A. But now I want the length also to be mod 3. I want length also to be mod 3. Let's not forget that. So if I reach here, I've already seen 1A. Okay, my length, I've already seen 1 character. Look at this, I've already seen 1 character here. Actually, let's use a slightly different notation. Instead of calling this Q0, Q1, let's use a different notation, right? Let's call this S0 and S1. Okay, because again, so that we'll have a better way of representing it. Again, S0, S1 here is all about starting string parts. Okay, so the whole model or the states which correspond to the string components, like the string should start with A. Okay, I'm writing it here. Everything that I need to do with the modulo operator, I will actually use Q0, Q1, Q2. Of course, my start state is this. My start state is not Q0 here. Okay, so because I have modulo 3, I have to track reminder 1, reminder 2, reminder 0. So if I have arrived here, right, my length is already 1. Okay, so this has to be Q1. Again, corresponding to reminder 1, I'll have Q1. Corresponding to reminder 0, I'll have Q0. Corresponding to length 2, I will have Q2. Okay, look at this. I'm giving different names. S0, S1 are states that correspond to the first part. Okay, so for this part, I will have Q0, Q1, Q2. For this part, I'll have S0, S1. Okay, this way I can break the problem into two components. That's why I'm using a different color also. Okay, so now this is good. This is tracking that, and now I have odd. I have one here. What happens now? I have one, but the length of my string is 1 now. Okay, and it's a valid string already because the first condition is satisfied by the time I arrive here. Now let's look at the string modulo. So if you think about the string modulo part, how does the whole thing work? String modulos work like this, right? String modulos, again, this is string length modulos, sorry, because what we are looking for is length modulos. Length modulos typically have this structure. Okay, so the lengths typically have this structure, so length modulos will change them. Okay, so now if I encounter, look at this, I encountered one string here. Okay, let's actually write this down. String length is 1, string length is 2 now. Okay, whether I encounter A or B, string length is 2. This part anyway takes care of starting with A case. Okay, now if I encounter Q3 or Q0, let's call it Q0. Okay, if I encounter, so here my reminder is 0. Okay, let me write that in a different color. Here my reminder is 0. So this has to be a final state. So let's make it a final state. Because what do we want? I want 0 mod 3. Right? I want 0 mod 3. Right? Now look at this. Now so this is my Q0 corresponding to the length being divisible by 3, Q1 length with a remainder of 1, length with a remainder of 2. Till now everything is looking good. So now what if I have A comma B? What happens now? See, now the length here is 0, or of course length cannot be 0 because it has to start with A. So 0 is not a possibility. Length is 3, length is 6, length is 9, length is 12, so on and so forth. But now when length becomes 4, where should I go? I should go here because this state basically says that the remainder is 1. Remainder is 1, 4, 7, 10. Again, this is again 1. I'm tracking 1 mod 3 here. This state is tracking 1 mod 3. This state is tracking 0 mod 3 as we discussed here. 0, Q0, 1, Q1, 2, Q2. Okay, so similarly 2, 5, 8, 11, so on and so forth, which is 2 mod 3. So if you think about this whole diagram, it has two components. You can think of this as the first component. This first component takes care of starting with A. This is your second component. The second component takes care of your modulo part. And we just added these two pieces using this transition. Now on this state transition AB, on this state transition AB, on this state transition AB, yes, all state transitions are there. Of course, I have a dead state because I always wanted to start with A. If it starts with B, I don't care whatever is the length, I will never accept it. Look at this. Look at two pieces. Look at how two finite automatas, you can think of it as finite automata 1, finite automata 2, how both of them got joined here. Because we have two conditions and we have two logical automata connecting two. See, for this I can draw an automata, for this I can draw an automata. Now I'm combining both of them intuitively by using this arc, right? So let's go one step further now. What if I want strings that starts with AB and length is 2 mod 4? So first draw for AB. Okay, first let's draw for AB. Okay, for AB, what should it be? I am at Q0. If I encounter A, Q1. Okay, instead of using Qs here, because we'll use Qs for the reminders here. Let's call it S0, S1, AB, right? So S2. Now when I reach here, yes, from here on, everything is good because it starts with AB now. If it starts with B here, I should reach a dead state. Okay, let's call it S3. S3 is a dead state. Okay, because if it starts with B, I'll not care about it, right? Similarly, if it starts with AA, look at this. If it starts with AA, I'll reach a dead state here. This is my dead state. So this diagram drawn in yellow corresponds to this. Okay, let me draw it in a different color here. I'll draw in orange. So this part I'll draw it in orange, right? See, by the time I arrive here, I've already seen two characters. See, I have mod 4. When I have mod 4, 0, 1, 2, 3. This is going to be my final state, right? This is going to be my final state. So I'll create Q0 corresponding to it, Q1 corresponding to it, Q2 corresponding to it, and Q3 corresponding to it. Okay, let's start here. So by the time I arrive here, look at this. By the time I arrive here, I've already seen AB. Okay, I've already seen AB. So what I can do here, actually, I don't have to create S3 here. I don't have to see. By the time I arrive here, I've already seen AB. Okay, now okay, let me change the color again. I'm sorry, I forgot about the colors. Okay, so by the time I reach here, I've already seen 2 characters, right? And what I want is 2 mod 4. So this will be Q2, right? Because I've already seen 2 characters, which means the length right now is 2 mod 4. The length is already 2 mod 4. The length right now is, what is 2 mod 4? 2, 6, 10, so on and so forth. The length is already 2, right? Now we'll go from here. Okay, I need again 4 states. If I have Q2 here, I need Q3, I need Q0, and I need Q1. Because I have mod 4, I need 4 states. So whether I get A or B, I go here. Whether I get A or B, I go here. Whether I get A or B, I go here. Look at this. From reminder 2, if I get one more character, I go to reminder 3. From reminder 3, if I get one more character, I go to reminder 0. From this, I go to reminder 1. Look at this. From here, I'll go to this. That's it. That's all there is. Now again, here there are 2 parts. This part corresponds to starting with AB. This part corresponds to the modulo part. Very simple case here. We are just combining 2 automata logically using this arc. Okay, that's the elegant and beautiful part here. Let's look at one more example here, right? So what if I wanted to start with ABB and 1 modulo 5? Okay, this is the last example. With these combinations, you'll understand it perfectly. Again, I'll use different colors here. Okay, I'll use green here. Okay, let's use green here. Very simple. Q0, sorry, let me use S0s here instead of Q0s, right? S0, okay, A, S1, B, S2, that's it, A, B, B. So if ABB is there, I go to the next part. I have 2 parts here, right? Starting with ABB, then I'll have the modulo based finite automata here. Now if it doesn't start with ABB, if it starts with B here, or if there is A here, or if there is A here, I'll reach this dead state here, right? This is my dead state. What is this dead state? S3. Okay, let me just add these like this. Okay, because the moment I arrive here, I'm seeing AA. Of course, it should start with ABB. Only ABB, only this part is valid, right? So once I reach here, now look at this. For 5, I have 5 possible states. Reminder 0, 1, 2, 3, 4. Similarly, Q0. For this, we'll do Q0, Q1, Q2, Q3, and Q4. Now, by the time I reach here, I've already seen 3 characters, which means this should be Q3, right? I've already seen 3 characters here. So this should be Q3. From Q3, if I see one more character, I should go to Q4. If I see one more character here, I should go to Q0. Because after 4, if you add one more character, you should go to 0. Right? So from here, I should go to Q1. Right? From here, I should go to Q2. Okay, back here. Again, this will be AB, this will be AB, this will be AB. Now, I want 1 mod 5, which means this has to be my final state. 1 mod 5, right? So this has to be my final state. So the string, again, 2 parts here. This automata checks whether it starts with ABB or not. This checks the modulo part, right? With so many examples. Oh, there is one more example. I'm sorry. There is one more example I want to walk you through. Okay, actually this example is very good. Okay, sorry. I think this is the last example. Yes, this is the last example. Okay, but I want to cover all the cases, as many as I can. Okay, so here you have 0 mod 2 or 0 mod 3. Look at this, 0 mod 2 or 0 mod 3. What is 0 mod 2? 0, 2, 4, 6, 8, 10, all of them. What is 0 mod 3? 0 mod 3 is 0, 3, 6, 9, 12, so on and so forth. Obviously, you have everything that is a multiple of 6 will be there in both, because the LCM of 2 and 3 is 6, right? So how do we build something like this? Let's go. Very good. Again, the length here should be, okay, let's write this down. The length here should be 0, 2, 3, 4, 6, 8, 10, 12, 14, 15, 16, so on and so forth. How do we build something like this? Look at this. I want 0 first. Let's start building it, right? 0 is anyway there, so Q0 will be there. Okay, now length 1 is not there. Look at this, length 1 is not there. So this will not be my final state. So this is length 0, length 1. Length 2's have to be there. Look at this. If my length is 2 or a multiple of 2, it has to be there. Very good. So till now we have reached. So if the length is 3, see either 0 mod 2 or 0 mod 3, which means divisible by 2 or divisible by 3. Okay, divisible by 2 we have it. If we have divisible by 3 also, we will have it. What is there? Okay. Now what about divisible by 4? Look at this. I have 2 and 3. 2 cases I have. So I would actually end up needing 6 states for this. Because I don't want to accept 5. Remember, 5 I don't want to accept. See, what all do I don't want to accept? 1 I don't want to accept. Okay. 2 I want to accept. 3 I want to accept. 5 I don't want to accept. 6 I want to accept. 4 I want to accept. Okay. Now if I get one more character, Q4, yes, I want to accept this. Because you have all multiples of 4 anyway. 4, 8, 12, all of them are there. You have all multiples of 2 here. You have all multiples of 2. You have all multiples of 3, all multiples of 4. But all multiples of 5 you don't want to accept. Okay, so this is not a final state. Now all multiples of 6, again you want to accept, right? Anyway you will do it here. All multiples of 6 you want to accept. Anyway, the LCM of both of them, the LCM of 2, 3 equals to 6. So that's why you need 6 states here to keep track of all the possibilities. Look at this. This is a very, very interesting thing. You have 0 mod 2 or 0 mod 3. If it was 0 mod 2 and 0 mod 3. Okay, look at this. If it was slightly different. If it was 0 mod 2, which means divisible by 2 and 0 mod 3. This basically implies 0 mod 6. If you had a case like this is nothing but 0 mod 6, right? Because it has to be divisible both by 2 and 3. That's what it means, right? That's the meaning of LCM, right? If a number is divisible by both 2 and 3, it will be divisible by 6. And so if this was not or and, you would build a simple model which is 0 mod 6. This is actually 0 mod 6 if only this was the final state. This is not a final state, this is not a final state, this is not a final state. Then imagine if Q2, Q3, Q4 are not final states, only Q0 is final state, this model is actually 0 mod 6. But we have logical OR here, not AND. We have logical OR, right? Because we have logical OR here, you need to, this corresponds to 0, yes. 1 cannot be final state, 2 final state, 3 final state, 4 final state, 5 cannot be a final state, right? 6 again is a final state. 7 again is not a final state. 8 is again a final state because 8 is divisible by 2, right? And so on and so forth, right? So if you have the logical OR, only then things get tricky. But the number of states you need is the LCM of 2, 3. We can generalize it. If these are two prime numbers, the number of states we will need, because they're two prime numbers, the number of states we need is equal to the LCM of both of them, which means the product of both of them. If these two are co-primes, right, which means there is no common factor for both of them. Right? That's what, when these two are primes, what happens? There is no common factor for both of them. When there is no common factor, the LCM equal to the product of both of them. Right? Very interesting case. But I also wanted to cover this case of AND. If it is AND, it would have been 0 mod 6. Again, look at how many modulo based arithmetic models or finite automata we have studied. Again, the reason for covering these many models over the last 4 or 5 videos is so that you can build any finite automaton of any of these cases.